Okay, so sorry about the delay. I had some problems with the video. It's working out. So how's everybody doing today? All right. Okay. So a couple things I want to announce. One is there's a quiz coming next week. So I put the upcoming because I've had questions on this. I should have done this before. Next quiz is 1 week from today, Monday. Then the one after that is 2 weeks from then, 2 weeks from then again, and 2 weeks from that point. And then the final exam is on December 13th. That's a Thursday, not a Monday. Any questions about that? So we will try to finish the material for quiz 3 today, as much as possible. And what I've done, I've put in more practice problems. So you now have, if this link works, what's wrong with my connection? Let's see. You have, all right, what I'll do is I'll try to give a list of the problems that I think would be most useful to practice on. But there's these practice problems 2B, 2C, 2D, 2E, 2F. Then there are some problems on momentum that we're covering today from the practice problems 3B, 3C, 3D, 3E, 3F. Okay. These are midterms from a class that I taught before. There's several hundred problems here that you can work through. They're all pretty much suitable for the quiz. Now, one thing I want to mention, so how is the homework going for you guys?
Last one was rough.
Yeah, it's pretty tough. So I agree that the homework is tough. So I didn't write the homework problems. I'm coming into this with the way the course is taught. So I'm not trying to change things up. Homework is good, but it's heavy, and if you start it late, it could be overwhelming. You can't finish it. Okay? So a few things I want to say. One thing is people really do need to start earlier. I've been watching how much people are doing before Sunday, and it's really not very much at all. Okay? So as I said before, the homework during the week is pretty light. So typically, with some exceptions, the pre-class stuff is pretty light. You don't really have that much homework right during the week. Do you agree? It's not that much. So start doing the problems for the Sunday homework. Also pay attention to the difficulty level of the problems. If you don't want to spend your whole life doing the difficulty 4 level problems, maybe you don't need to do those until Sunday night and give them your best shot. Okay? Try the difficulty 1 and difficulty 2 problems first. Spend your time there. Most of the problems are difficulty 1 and 2. Then you have the 3 and the 4 that take more time, but there are not so many of those. Now the thing is, for the difficulty 3 and 4 problems, there are hints for all these things. Okay? So the hints don't cost you points. They just don't. If you solve a difficult problem without any of the hints, you get more than 100%. It's just when you use the hints, you don't get as much of the extra credit. That's all it is. So go ahead and press the hint. You can't do press the hint. The other thing I'm noticing is nobody's asking me questions, or very, very few of you are asking me any questions on the homework. I love asking questions, so ask me questions if you're stuck on something. Okay? So if you have some difficulty with the homework, don't just say, oh, this sucks, I'm going to skip it. Try to do something about it. Start earlier. Ask questions. Do hints. Focus on the problems that are low difficulty. There are solutions to this issue. Okay? Everybody's all right with that? Okay. The other thing I want to mention, the harder problems on the homework are not going to be the ones that we're going to test you on the quiz. So these more difficult homework problems are for you to learn through doing these problems, through the experience of doing these problems. Because in real life, you end up with problems that are kind of complicated, like the one with the block, with the wedge, and the thing is sliding, and how many forces the wedge pushes against the wall. That's kind of a complicated problem. Or the one with the board where you have the other tabs on top, and you want to know how fast or how hard you can press or pull the board so that the other block on the top just starts to slide. Okay, these are difficult problems, but they're actually the type of problems that you might want to solve in real life. Okay. So there are two, I guess, purple chips here on this turntable. And the question I want to ask is, if I rotate, so what I can do is I can actually show you this by putting it on the floor. And then let's bring this up. And let's get rid of this screen here. Let's autofocus it. All right. Beats that camera over there, which is not really working very well. So the question is, if I maybe make it a bit higher up, see more of it. Okay, the question is, if I rotate this turntable, which chip will fall off first? Think about it. The inner one or the outer one? Which one will start to slide first? So think about it intuitively. Make your prediction. And then try to think about what physics did you learn that might help us to not just guess about it. Okay? Think about it. All right, so use your physics knowledge, and now maybe update your guess. Put money on your table. Okay. All right. So let's go. Let's see what happens. Okay, let's go faster. Which one fell off first?
The outer one.
The outer one. Okay. Does that make sense to people? Let's do it again, just in case that was just a fluke. Okay, clearly the outer one. All right. Now, if you think back to childhood, how many of you have been on a merry-go-round that spins around? Okay, so you know when you want to really experience it, you go to the outer edge and you stick your head out, right? And that's where you really feel it. Right? If you're in the middle, it's not so, you just spin around and you go like this. And it's not much. When you go to the outer edge, you get the fun effect. Okay? So let's try to figure out why that is. Okay, let's think about, we talked about centripetal force, right? We have, let's say, an object goes around a circle. So it's going around a circle with a speed v, and at a radius r. Okay, so we know there's an acceleration, the centripetal acceleration, and the magnitude of the centripetal acceleration is, what's the formula? G squared over r. Okay, so that the centripetal force is just the net force required to keeping this object on the circle. So that must be m times a. So that'll be mv squared over r. Okay. What is providing the centripetal force for these chips? Friction. Yeah, exactly. Friction. Is it kinetic or static friction? Yeah. While they're not moving on the surface, there's no sliding. It would be static friction. When they do start to slide, it would be kinetic friction. All right, so now, in order to figure out which chip will fall faster, we have to figure out B and R for these cases. So you might think, okay, because R is bigger for the chip that's further away, okay, that the required net force is smaller, right? You might think that. That's actually wrong, but you might think that. And that would give you the wrong answer. You would think that it would be easier to keep the chip on the outside on because this v squared over r, the r would be bigger for that case. Okay. The reason why that's wrong is because v is also bigger in that case as well. Does everybody understand? Okay. So the thing that's the same for these two chips as they rotate is going to be not the velocity, but what? What will be the same for these as they look at their own? What kind of velocity? Yeah, the angular velocity. So omega for the two chips are the same. So omega, let's say 1 is equal to omega 2. So let's say this is the inner one, and this is the outer one, but they have the same omega. So they both are omega. Okay. So now when I try to figure out what is the speed of the inner one, the speed of the inner one will be the radius of the inner one times omega, whereas the speed of the outer one will be the outer radius times omega. Everybody's with me on that? And now if I calculate the required net force for 1, I get m, okay, let's take the masses of these to be the same, because there they are pretty much the same chips. Then I have v1 squared over r. Okay. So everybody's with me? I'm just plugging this in for first case 1. And then I will have m, then I'll have r1 times omega, I'm plugging this guy into here, squared over r1. And so I will get m, everybody's still following me? And then I have r1 times omega squared. Everybody's got that? Now if I do this for the net force required for number 2, then it's all the same thing. v2 squared over r2 is equal to m times, and then I'm going to replace this by r2 omega here. So I'll have r2 omega squared over r2. Then I have m r2 omega squared. Okay. So now you can see that the required net force for 2 will be bigger because it has a larger radius. And that's why it can't stay on, because the friction will be the same. These guys, the maximum factor is exactly the same. Okay, any questions about this? Good. Let's then cover some new material. We're going to talk about something completely different, and we're skipping around. To be honest with you, I'm not sure why we're doing it at this particular time, but that's the plan, that we're going to jump to chapter 11 for a little bit, but not fully quite yet. We're going to jump back to chapter 9 later. And we're talking about linear momentum. Okay. So, the idea of linear momentum, I think I've said this example before. If I were to take an object like this, and I were to toss it to you about 10 meters per second, you wouldn't really worry too much. It would be annoying because the professor's throwing stuff at students that it wouldn't hurt. Okay? But if there was a truck coming at you at 10 meters per second, you would get out of the way. I mentioned this in the context of inertia. I can also talk about something called momentum. And the reason why you worry about the truck going at 10 meters per second versus the ship going 10 meters per second is because the truck has a lot more momentum. Okay? And it's difficult to stop something with a lot of momentum because you'll get hurt, basically. Okay? And so let's talk about the linear momentum for an object. It's a vector. The linear momentum for an object is small p is equal to small m the mass times v. Okay, so this is the linear momentum. This is the mass of the object, and this is the velocity. So if the object has a lot of mass, or more mass, it has more momentum, but it has to be moving. So if it's going faster, then it also has more momentum. So it's a vector, and it has units. It is a vector. It has units of, okay, we can figure it out. Mass has units of kilograms. Velocity has units of meters per second. So units is kilograms meters per second. Okay. Any questions? All right, so why is this momentum thing useful? Well, we're going to see that it's related. If I think about how the momentum changes, it's going to be related to forces. Okay, so we're going to take a time derivative of the momentum. Okay, let's take the time derivative. Okay, so I have dp by dt. So by this time, everybody's who's doing the calculus, or you're okay with derivatives by now, right? Everybody's gotten past that one. Okay. So I'm going to take the derivative d by dt of m times v. And in most of the applications, most of the problems we're going to consider, it's going to be, like a ball. Well, it's going to catch a ball moving through space, or me running, or you. It's, the mass will not change. Okay? And so there's one exception. One exception is maybe if it's a rocket and it's shooting fuel out of the back end. That's another. It's a very special case. But most of the time, the mass of the object that's moving doesn't change. Okay, so this m is going to be constant in most cases. Almost every case except for a rocket, actually, I should say. And so the time derivative only acts on the velocity. So we have m times dv by dt. Okay. And since, so what is dv by dt? Yeah, that's the acceleration, right? The time derivative of the velocity is the acceleration. So we have acceleration. So we have m times a. Okay, that's kind of nice. M times a, that should sound familiar. We did that with Newton's second law. So we can write Newton's second law. We can write Newton's second law as F net, the way we wrote it before, is equal to m times a. But we just found that m times a is also the time derivative of the momentum. So the net force is how much you can change the momentum with time. So F net is equal to derivative of p with respect to t. Any questions about that? Everybody's okay with that? Okay, so now let's consider a special case where the net force is 0. Oops, it's a formula sheet. The thing is, after you take your quizzes, you turn in your formula sheets. The reason I keep them is I use them as scrap paper. It's not some secret. It's just use it as scrap paper. Trying to conserve resources. Okay. So if the net force on an object is 0, then what do we conclude? So we said F net is equal to dp by dt. So if the net force is 0, that means dp by dt, the time derivative of p is equal to 0. Okay, that's what we conclude. Now, if I say the time derivative of something is 0, yeah. Yeah, I was going to just ask for volunteer. You read my mind. Exactly. So if the time derivative of momentum is 0, then the momentum is constant. Okay, so then we say that the momentum P is a constant. It doesn't change with time. Okay, very good. All right, so now, yeah, question. Oh, sorry, it's a little too high. Yeah. Okay, so how do we use this? Okay, so let's write conservation of momentum. Technically, it's called linear momentum. I'm just using a shorthand calling it momentum. Later on, we'll talk about something called angular momentum, but we're not there yet. Okay, so suppose I have, since I have these chips here in my group, I have two objects and they collide with each other, okay? They bang into each other and they bounce off and do something complicated, all right? So if I think about these two poker chips and suppose they're an isolated system, they're going to interact with each other, but there's nothing else that's really affecting their motion. Okay? So you can imagine maybe this is a frictionless surface like an air hockey table, and then I was to send these into each other, they would bounce off, they would do something, or maybe they bounce head on and bounce backwards like this. So there's this notion of the conservation of momentum, and it's just simply the statement that the total momentum of an isolated system remains constant. Okay. Whatever you have in the beginning, the total momentum of the system will be the total momentum of the system that you have at the end. Okay, so now you might say, how do we use this? Okay, so let's see. Let me just draw a picture. So typically in these problems with momentum, there's some collision. Something happens. Something bangs together. The reason why is because if nothing happens, it's kind of trivial. If an object's moving, it doesn't hit anything. It just keeps moving with that velocity. Now, who needs an analysis for that? We already know what's going on there. Okay, so we typically have two objects, or maybe more than two objects involved. And so we have some initial setup. And the initial setup, we have, let's say, a mass m1. That's the mass of the first guy. And it has some velocity. And, okay, I need an I for initial, so there'll be two subscripts here. And I need a 1 to distinguish that this is the first object. So I will call this v1I for initial. Okay? And then let's say we have another object with a mass m2. And we will have, that will be coming in with some initial velocity, 2I. All right. Any questions about this? And now what we're going to do is talk about the final setup. We have M1. And it has some final velocity, 1 final. And then M2. And it has some final velocity. Okay. So this is some collision. I've drawn them so that they're hitting head on and they're going this direction, but they could go off in some direction like this. And so the equation for conservation of momentum is that the total momentum initial, so let me write on this side the total initial momentum. And then I have the total final momentum on this side. They will be equal. So what is the total initial momentum? I take the momentum of the first object, mass times velocity. So I have m1 times v1I. Okay. Then I have the second object. I have m2 times v2I. And then I have the final momentum. So I have m1 v1 final. Okay. And then I have m2 v2 final. So these must be equal to each other. Questions about this? So in particular, suppose that I had a very simple situation. Let's consider now it wasn't like a collision like this, but let's just imagine that this was that I have these chips here, and I put a little bit. Let's say this little thing here was a stick of dynamite, okay, between these. Just imagine, and it explodes, right? And then these objects, they would go in some direction like this. The fact that the initial momentum of the system was 0, is everybody agrees that it was 0 because they weren't moving? Okay. Because the initial total momentum was 0, the total momentum of the final system, even though they're going really very fast, has to be 0. Okay? Because of conservation of the total momentum. Any questions about that? So whatever momentum this guy has, this one must have the opposite magnitude, the same magnitude but opposite direction for the momentum. Okay. Okay, now, if everything is aligned along the x-axis, if everything is aligned along the x-axis, then I'm going to put x's, all right, so I'm running out of space here. I already sort of put 2 subscripts here. I'm going to put the x as a superscript, okay, just because I'm running out of space. So then I can write m1 v1I initial x component plus m2 v2I x component is equal to m1 v1 final x component plus m2 v2 final x component. Okay. Everybody's with me? Now, if it's not all along the x-axis, then we also have to take a look at the x components as well, which you can fill in the blanks. You put the y's instead of x's. Okay, it's not really that hard to figure this out. And you do it for the z components as well if it's in the z direction. Okay. Everybody follow me? Good. Okay, now the next topic I'm going to talk about is something called impulse. All right. So when something collides, very often, so a great example is a baseball bat. When you, this is the only ball I have here. But when a baseball bat hits the ball, okay, there's this impact where the ball was not, maybe it was going this way, and then all of a sudden it changes its direction very, very quickly. Okay. We talk about this type of equation, and we use the word impulse, and we even give a name for the change in momentum caused by this impact. So let me tell you about that. So impulse. Okay. To be honest with you, this definition of impulse is kind of not necessary. It will turn out the impulse is really only the change in the momentum, but historically this is what we call it. So the impulse, and it even gets its own name, capital J. I don't know why it's a capital J, but it's what it's called. The impulse, capital J, of a force is the change in momentum delta t caused by the force. Okay, so J is simply delta t, change in momentum. So impulse is equal to change in momentum. All right, now we can do a little bit of math to write down another formula. Okay, so let me just sketch out the derivation. So if I have that F is equal to ma, okay, we're just considering one force. There's only one force acting, one force involved acting. If there's only one force acting, then that will also be the net force. So F is equal to ma, and this is also equal to the time derivative of the momentum. So what I'm going to do is I'm going to write down a formula for the impulse. The impulse is the change in the momentum, or P final minus P initial. Okay. And now what I'm going to do is I'm going to take the integral, the time integral of the time derivative. All right, I'll show you. So what I can do, P final minus P initial can also be written as the integral from the initial time to the final time of the time derivative of P. If you don't believe me, just think about what you would get if you did this silly integral, right? You have a time derivative, you get the antiderivative, which is P, will work just fine. And then you just evaluate P at final time minus P at initial time. Okay. But we said this dP by dt, that just will be equal to the force, F here. And so now we have the relation that the impulse is the time integral of the force from the initial time to the final time. Okay. So for a collision along the x-axis, we could write down J x component is equal to the integral of the x component of f dt from the initial time to the final time. And if you want to do this in terms of pictures, if we were to plot, oops, too high. If we were to plot time here, let's say this is the initial time, this is the final time, and this is the function, the force, the function of time. And let's say it has some behavior like this. You get some force between these two times. Maybe that's the force exerted by the baseball bat on the baseball. And typically in these problems, when we talk about impulse, we're talking about a very short time interval. The concept of an impulse is there's a snap, and then it's only maybe a millisecond of time. And then as a result, there's a change of momentum. So what we derived is that the integral under this curve, the Jx, is the area under the Fx versus t curve. Okay. So if you draw the force versus time and you integrate it, area under the curve is equal to the impulse. Okay, any questions about this? All right, let us, let's see. Let's do a quicker problem. Let's pull another, maybe something over. Okay, here's the question. Two blocks are connected together by a rope. By the way, I'm getting my collector problems from this whole bank of test problems I have in the practice problems. So if you want to get a jump start on the collector problems, start doing those practice problems. Okay? So the two blocks are connected by a rope and another rope is attached as shown. I'm going to draw a figure in just a minute. Okay. If there's no friction, what is the acceleration of the blocks? Along the ground. So it's on the ground. Okay, so we have a block here, and this is M1. We have another block here, and this is M2. M1 is equal to 2.0 kilograms, and M2 is equal to 4.0 kilograms. And then we have a force that's going in this direction, F, and F is equal to 42 newtons. And then there is an angle here. I didn't really draw it to scale, but it's 60 degrees. This is, let's say, the positive x direction. We want to know the acceleration along that direction. Okay? And so the choices are A is 14 meters per second squared. B is 10.5 meters per second squared. C is 7.0 meters per second squared. D is 3.5 meters per second squared. E is 21.0 meters per second squared. Okay, and I'll open up the polling now. Just a second. It's open now. Okay. People are that done? I'll give you another 30 seconds.
Yeah.
Okay, if you haven't made a choice, go ahead and make your choice now. And let's see what people said. All right, a lot of people say D. So let's take a look. All right, so we have this rope. It's on the end. It's pulling both blocks. So it'll be simplest to consider both blocks together as a unit. Okay, if you did the one on this, then we have to worry about what is the tension in between, and you don't know that, so you have to solve. So it's much better to start off with the whole system first. That's sort of a general rule. When you have either you're pulling blocks, you're pushing blocks. You have several objects. Typically, you try to address the whole system first. Very often, that's the best strategy. Okay? Does everybody understand what I'm saying? Consider everything at once, all together at first. So that's what we will do. So we have these two together. And so this is equal to 6.0 kilograms for the whole thing together. And the only force that I really need to worry about, because I'm only going to go in the positive x direction, the acceleration is only horizontal. I really only need to consider this force F here, which is 42 newtons. I could, if I wanted to, also consider, I have the force of gravity, I have the normal force of this guy, force of gravity, normal force of that guy, but they just all cancel out to give 0. So that's kind of not a very interesting thing to do. Okay. If they ask what is the normal force on this block, then that's what you use to get the answer, but we don't need that for this. So now we have 60 degrees here, so I can get the x component of F. So that'll be 42 newtons times the cosine of 60 degrees, and that comes out to about 21 newtons. And so now I say that this is the net force in the x direction. So I have net force x is equal to 21 newtons is equal to the mass times the acceleration in the x direction, where the mass is the 6 kilograms. Okay. And so therefore I get the acceleration is 21 divided by 6. That's about 3.5 meters per second squared. All right. Okay, now, just before I let you go, there's one more question I wanted to ask you. In terms of preparing for the quiz, so I want to try to help you the way you would want to be helped. What would you like me to do that will help you prepare for the third quiz? We have a whole week. We've just covered all the topics. What could I do to help you, sort of give you the answers to the quiz that would help you prepare? Yeah. A lot of quicker questions? Okay. Practice problems?
Will we be able to take questions off of our homework to ask you to have to go over in class?
Sure. I can answer questions now. That's okay. I can answer this question. But what I can do, right, I know some of you do the practice quiz as practice, and you would not want me to actually do it in class because then it ruins the trick. So what I'm planning to do as a compromise is I'm going to record the solutions of me giving the solutions of the practice quiz online so you can see it when you want to see it. Does that work?
Yeah.
Okay. All right, I'll do that. So the practice quiz will be up later today. See you tomorrow.
So you're gonna make a video while you're solving the practice?
Yeah.
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 I emailed you about the
Okay, yeah. Did it work today? All right, so let us.